In this video, we are finally moving away from the diffusional transformation and start looking at Martensitic transformation. Specifically in this video, we'll look at Martensite characteristics, nucleation, and growth. Martensitic transformation is diffusion-less. Therefore, even when there are atoms moving around, their movement is constrained by the unit cell. In contrast, for diffusional phase transformation, atoms can move across many unit cells. In Martensitic transformation, the atoms move in a military march way. In contrast, for diffusional transformation, the atoms move in a random way. Let's look at a few examples of simplified Martensitic transformation. Martensitic transformation can accommodate dilation, shear, or shuffle. Again, in these simplified examples, you can see the Martensitic transformation, the atomic movements are limited or constrained by the unit cell, and the phase transformation is usually accompanied with a shape change. The most famous Martensitic transformation is probably in steel. At high temperature, steels have FCC structure. If you cool down the steel very fast, the atoms will reposition slightly and form martensite. Martensite has the BCT, body-centered tetragonal structure. During the Martensitic transformation, not only the iron atoms are locked, the carbon atoms are also not able to diffuse. In fact, the specific positions carbon occupy in FCC is a key feature that leads to Martensitic transformation. You can use various characterization techniques to reveal the Martensite microstructure. You can use optical microscopy. Also, you can use SEM-based techniques such as EBSD. And another common technique is to use regular bright field TEM. Regardless the microscopy technique you use, there's one common feature shared by all Martensite is they all exhibit the plate-like structure or lath-like structure. Most Martensite plates or laths are very thin. If you look at the scale bar in the TEM micrographs, they are 1 micron, and many Martensite plates or laths, they are only a few hundred nanometers in thickness. Here are some characteristics of Martensite and Martensitic transformation. Martensite are usually denoted as alpha prime. The parent austenite is denoted as gamma. In steel, Martensite is formed when the austenite is cooled down super fast. Second, there's an important concept called Martensite habit plane. The habit plane basically is the Martensite-austenite interface. The habit plane travels super fast at the speed of sound in solid that makes the capture of their movement extremely difficult. Moreover, the size of Martensite was observed to be independent of the austenite grain size. Rather, it is affected by chemistry. Here are two examples here. On the left, it's a low carbon steel, and on the right, it's medium carbon steel. The low carbon steel has much finer Martensite microstructure compared to the medium carbon steel. Next, Martensite has starting temperature and finishing temperature. It happens to austenite as well. What this tells us is when Martensite forms, it does not form altogether spontaneously. There are regions of the grain or parts of the component that will undergo Martensitic transformation first, followed by the rest of the material. Here shows the DSC data. DSC stands for differential scanning calorimetry. Let's have a look how to interpret the curve here. As you increase the temperature, initially there's no change in the heat flow. This tells us the sample remains Martensitic until this point, and then there's a peak indicating Martensite has transformed into austenite. Note the peak is pointing down, telling us the phase transformation is endothermic, it absorbs energy. As temperature further increases, the sample remains austenite, so the line stayed flat. Next, let's look at the cooling part. Again, initially, as you cool down the specimen, it remains austenite until you hit the Martensite starting temperature. After Martensitic transformation, the curve stays flat again, indicating there's no heat flow anymore. There are two things I'd like to draw your attention here. The first is, doesn't matter it's from Martensite to austenite or from austenite to Martensite, the phase transformation happens in the range of temperature. There's no one single temperature that drives all Martensite into austenite or austenite into Martensite. The second thing is, as you can see, the Martensite and austenite phase transformation temperatures are different. This is caused by the undercooling of the system to trigger Martensitic transformation, as well as the strain stored in the system. And the difference between those two peaks are termed as thermal hysteresis. Be aware that when you cool austenite down to Martensite, after the Martensite finishing temperature, the DSC curve remains flat. It doesn't necessarily mean all austenite turned into Martensite. Very often, you may see retained austenite in the microstructure. They do not transform into Martensite largely because of either the chemistry or the strain. The last thing I like to talk about regarding the characteristics of Martensite is the difference between Martensite laths and Martensite plates. For Martensite laths, there's no internal twins. There is high density of dislocations stored in those Martensite grains. In contrast, for Martensite plates, there are high density twins present in the Martensite grains. In the next slide, I took the video from Professor Harry Bhadeshia's website, and it's really from his YouTube channel. Here, it shows the Martensitic transformation of a steel when you cool the temperature down. I hope you can appreciate how fast Martensitic transformation can occur. After looking at the characteristics of Martensite and the Martensitic transformation, we can look at the Martensite nucleation and the growth. The Martensite nucleation is very unique. It does not happen from grain boundaries or surfaces. This is in contrast to diffusional transformation. Martensite nucleations are usually associated with dislocations in the crystal. It can be caused by the dislocation cause or by the strain field of dislocations. Let's look at this one by one. In the first example, the example on the left, you are looking at the 111 plane of an FCC crystal. You have the ABC stacking. So that's the first layer, the large circles. That's the second layer, small circles. And third layer by the triangles. That's the ABC stacking. If the third layer does a twinning shear, it will locally turn the FCC structure into a more like BCC structure, leading to the Martensitic transformation. Martensitic transformation can also be assisted by an intermediate phase. Instead of going directly from gamma to alpha prime, it can go from gamma to epsilon prime to alpha prime, and the epsilon prime has the HCP crystal structure. The two-step shear of the second layer of the atoms, as shown in the figure on the right, shows how locally it can change the FCC structure into HCP structure. The third layer atoms then shuffle to complete the Martensitic transformation. In addition to dislocation cause, the strain field around dislocations are believed to affect Martensite nucleations as well. In the example shown here, there's a dislocation dipole, and the region between those two dislocations is highly strained, and the strain can favor Martensitic transformation as well. It is interesting to mention that external strain can play a huge role on the Martensite variant. If you apply an external load on the material while cooling down, the Martensite variance you obtain here will be different from the strain-free condition. After looking at Martensite nucleation, let's move on to look at martensite growth. The growth of martensite is governed by the nucleation, the glide of those disconnections or ledges on the habit plane or the austenite-martensite interface. Since usually there's a volumetric change when there's martensitic transformation, there's strain stored at the martensite-austenite interface. The nucleation of those disconnections or ledges relaxes the elastic strain, and the glide of those disconnections or ledges pushes martensite a few atomic layers into austenite. This nucleation then glide process repeat, and eventually martensite can consume austenite. The growth mechanisms I just mentioned is very similar to what people observed in mechanical twinning or deformation twinning, how the twin boundary migration happens. In fact, there are many similarities between martensitic transformation and deformation twinning. The last thing I'd like to briefly touch upon on this slide is the martensite-austenite interfaces. In some cases, they do not lie on low index planes. In some extreme cases, there's simply no well-defined plane that the habit plane lies on. This is in contrast to twinning, because twinning usually has a well-defined twin plane. Before wrapping up today's slides, I want to say that martensitic transformation is not something unique in metals and alloys. They are also observed in ceramic systems such as zirconia, as well as vanadium dioxide. Here is one crazy example I learned from Professor Harry Bhadeshia's lectures. We know that some viruses, when they attach on the cell surface, they can inject a needle into the cell body and eject the RNA into the cell to duplicate their genetic materials. The protein that is responsible for the needle injection is also governed by martensitic transformation. This is definitely some crazy stuff to me when I first learned about it. In the next video, we'll look at two examples to learn how scientists and engineers they take advantage of martensitic transformation to design tougher steels and shape memory alloys.